got a request to go through this problem. It's from Sapling Homework 5, question 20. And I want to frame it in the view of trying to decide what equations to use. I get a lot of questions about, there's so many equations, I'm not sure when I should use what. So we have three major tools in this class. We have conservation of momentum, initial momentum equals final momentum. We have Newton's second law. The net force on a mass m causes it to accelerate with acceleration a. And we have conservation of energy. E initial equals E final. So you might be saying, well, what happened to kinematics? So kinematics is a special case of F equals ma. So you can only use the kinematic equations when the a is constant in F equals ma. But this equation is really what tells you how an object moves over time. So it just tells you that if you know the force on an object at any time, you can figure out how it will accelerate, and acceleration is related to velocity, which is related to position. So if you have a case where the net force on an object is constant, you can use the kinematic equations, because that means A will be constant. And the kinematic equations are right there. Okay, so obviously you have to know when you're allowed to use all of these different equations, and that's where things get a little more complicated. But it's not that bad. So let's take a look at this question and see if we can figure out what of these main things apply here. So this question says you're designing a roller coaster as shown in the figure, and just general problem solving tips. I read the question usually a couple of times and write down pieces of information as I find them. So it says, previous sections of the ride give the train a speed of 10.7 meters per second at the top of the incline. Okay, so that's saying that when the coaster is here at point A, it has a speed of 10.7 meters per second. And I'm going to put a little sub a on that so I know that it's the speed at point A. And then it says this point is h equals 39.1 meters above the ground. Okay, so if we measure from the ground up to the roller coaster, this is h equals 39.1 meters. And let's call that HA. Okay, so you're keeping safety in mind, okay. The safety regulations state that the rider's centripetal acceleration should be no more than 1.57 g at the top of the hump. Okay, so here, the acceleration at point C has to be less than 1.57 g. And it has to be less than 5.21 g at the top of the loop. So the acceleration at point D has to be less than 5.21 g. Oh, no, at the bottom of the loop. See, that's why it's important to read the question more than once. So it's no more than 5.21 g at the bottom of the loop. Okay, for this initial phase of your design, you decide to ignore the effects of friction and air resistance. Ignoring the effects of friction and air resistance. So what does that tell you? Well, it means we're not going to have any forces of friction or air resistance. And it also tells us that energy is conserved, because there's no force here that's going to create heat if there's no friction and there's no air resistance. So this tells us that energy is conserved. All the forces acting here are conservative forces like gravity, or the normal force. Well, it's not technically it does no work, but we won't get into that until chapter 6. Okay, so now it's asking, what is the minimum radius you can use for the semicircular hump? Okay, so we have a semicircular hump here, and there's the radius r. Okay. So what do we do? And I guess I should call this r hump, since that's what it is in the problem. So what do we do? Well, let's first take a look at what we're after. So we want to find the minimum radius, and our constraint in this problem is that the acceleration at this point has to be less than a certain value. So usually when something says less or just or something like that, you're at a threshold between 2 points. And usually you can just put whatever value they're giving you for that quantity of interest in. So let's assume that our acceleration at this point is 1.57 g. So what creates this acceleration? Well, there's gravity, and this thing is moving in a circle. And we know that if things move in a circle, then the acceleration of something moving in a circle is the speed squared divided by the radius of the circle. So this thing is moving in a circle. So this is going to be the acceleration at that point. It's going to depend on the speed, it's going to depend on how fast it's going, and it's going to depend on the radius of the hump. So if you go really slow, the acceleration will be less. Okay, but how do we know how fast it's going? Well, we don't know it right now, but what's going to determine how fast it's going at that point? Well, it's going to depend on how fast this thing was going over here and how tall this is. So if it's taller, you're going to get going faster. So we said energy was conserved, and I think that that might be a good way to figure out what this speed here is. So if we're going to use energy conservation, we need to conserve energy between 2 points. So I'm going to pick point A and point C. Okay, so what does energy conservation say? Energy conservation says that the energy at point A, energy conservation says that the energy at point A is equal to the energy at point C. Okay, so let me get my energy conservation card. So E initial equals E final. So A is the initial and C is the final. Let's flip this over. So we've learned about 3 kinds of energy so far: kinetic energy and potential. So let's look at point A. Is there kinetic energy at point A? Yes, it's moving with speed v, so we have 1/2 mva squared at point A for kinetic energy. And is there potential energy at point A? There's no spring here, but it is a distance above the ground. So we're going to add the potential energy, mgy at point A in. And that's it for point A. At point C, is there kinetic energy? Yes, it's moving at some speed. We don't know what that is, but we're looking for it. So this should be 1/2 mvc squared. And then we also need to add in the potential energy because it is off the ground. So we need to add in mgy at point C. So now notice that the masses cancel. Okay, so let's just rewrite that. 1/2 VA squared plus GYA equals 1/2 VC squared plus GYC. Okay, so VA we know, G we know, YA. What's the height at point A? Well, if we define this as y equals 0, YA is just h. So 1/2 VA squared plus GH equals 1/2 VC squared, we don't know that, plus G times YC. So what's the height at point C? Well, it's just the radius of this hump. Okay, so this is our equation we got from conservation of energy, and we said that the acceleration of something moving in a circle is v squared over r. So at point C, the acceleration is the velocity at c squared over r. All right, so now we have two equations, and let's count how many things we know. So 1/2 is just a number. We know this. We know this. We know HA. 1/2 is fine. BC, we don't know that, so I'm going to circle it. And G, we know. And our hump, this is what we're looking for. Our hump is what we're looking for. So AC, do we know that? So actually we do. That's the thing we have a constraint on. We have AC is 1.57 G. So we know that. VC, don't know, I'll put that in a circle. And what's the radius at C? Well, the radius at C is our hump. And we don't know that, but we're looking for it. So we have two equations, but two unknowns, our hump and VC squared. So I'm going to solve this equation for VC squared and then plug it into this one. So we'll take this and we'll plug it in for VC squared in this equation. Okay, so now we're ready to solve for our hump. So our hump is in both of these terms on the right. So I'm going to pull it out. Okay, and now to get our hump by itself, we're just going to divide both sides by this term. So our hump will be what's on this side, 1/2 VA squared plus GH divided by this, 1/2 AC plus G. Okay, so now it's time to plug in any numbers that we have. So you could go ahead and do that. You could do it in Python, you could do it in your calculator. Doesn't matter to me. Note that there's a G that appears in AC, so you have to make sure you put that in. So this would be 1/2 times 10.7 meters per second squared plus 9.81 meters per second squared times H, which was 39.1 meters. Now we're going to divide by 1/2 times AC. What was AC? It was 1.57 times G, again. And then we need to add G one more time. So that's probably not the most efficient way to plug it into your calculator, but it'll work. That's it.